Today we're looking at voltaic cells. So what we did last time was we remember how to balance half reactions, right? There are quite a few of those on the homework for the last assignment, as well as finding voltages, standard voltage, by figuring out what's oxidized, what's reduced, getting the voltages from the table, flipping the oxidation one, and adding them up. So that's kind of where we're at. And where we're going to use all that stuff is in our construction of voltaic cells, also known as batteries. So the world of electrochemistry is electrochemical cells are split into two. We have two types. We have the types that have a positive E naught, and then we have the types that have a negative E naught. These are our non-spontaneous ones, which we'll cover at the end of this unit. Today we're looking at our spontaneous cells, known as batteries. They're also known as galvanic cells, and they're also known as voltaic cells. So all that stuff means the same thing. So just think about batteries at the grocery store, positive 9 volt. You don't buy a negative 9 volt battery, so you forget. That's one way to remember it. Okay? So what we need to be able to do is construct a cell, label all its components, talk about direction of electron flow, talk about overall voltage of the cell, and then talk about any sort of ion migration that happens within the salt bridge. You're never going to have to outright draw a cell on the AP. It's never going to be the case, but there have been times where you were given a cell and had to label significant amounts of different parts, putting ion migration on there, showing electron flow. And so by actually being able to draw it yourself, there's nothing that they'll throw at you that you won't be able to handle. So we're going to practice by drawing. So looking at this one, we are first going to find the voltage here, because in this problem, if you look, draw a diagram of the cells. In each case, label the anode and cathode, and I'm not going to read through the whole list. We have to do all that stuff, which we will. But then it says to calculate E naught. So I want to kind of get that out of the way. How would I find E of that reaction? What would be my first step? Correct. Write the half reaction. So I'm going to start with the cobalt just because it's first. Cobalt goes to cobalt plus 2. So to balance that half reaction, I put 2 electrons. And my other half reaction is copper plus 2 going to copper. So to balance that, I'm going to put 2 electrons there. Okay? So now we have to look up our voltages. Cobalt to cobalt plus 2, is that oxidation or reduction? Let's review that. This is oxidation because charge is going up. This is reduction because charge is reduced. Charge is reduced in reduction. So on the actual table of the reduction, I know that's the copper. You're going to find that equation exactly as it is, and we're going to take that value of 0.34 volts. So someone, I don't know the cobalt by heart. Was it negative 0.277? Okay, so off of the table, this comes out to be negative 0.277, but because it was flipped, you're not going to find it as oxidation on that table. We'll change the sign. So what is our voltage for this cell? 617? 0.617 volts. If we want to round to the right number of decimals, we'd say 0.62 volts. All right, so that's the first part done. I'm glad we have that over with. As far as balancing this equation, 2 electrons are lost and gained. So that original equation that we saw was balanced. The importance of that will be apparent tomorrow when we talk about the Nernst equation and changing concentrations and stuff. You'll need to have that equation balanced for the coefficients. All right, y'all ready to draw? Voltaic cells have 2 half cells, and they're in separate containers. In each half cell, we have some sort of solution, and we have some sort of electrode. Our electrodes are normally solid. If you have any weird examples in your homework that are gas, you can hang some sort of balloon-like semi-permeable membrane filled with gas, and you can have osmosis across the membrane and kind of have the same situation. But most commonly our electrodes, at least on the AP, they're going to show up, they're solid. What components do we use? Well, it depends on what half reaction we're dealing with in each of the containers. What half reaction do you want to put in the left container? Cobalt. So for now, and I think it's just, I think forever and for always, I think it's a good mode of operation to always write the half reaction underneath, because you can see what's going on in the cell. So in this cell, we have cobalt solid turning into cobalt plus 2 ions. So the components in this cell, your electrode is actually made out of copper solid. Your solution then is a solution that contains cobalt plus 2 ions. Now, is it really cobalt plus 2 in a bottle? No, it's probably cobalt 2 nitrate or cobalt 2 chloride or something like that. But those are spectators. All we care about is the cobalt ion. And I say 1 molar because look at that E. That E that we determined, you see it's got a little knot there, that little standard conditions in cells are not only 1 ATM and 298 K, it's also 1 molar solutions. So that voltage is only good if your solutions are 1 molar. All right, and so that would mean this would be our copper half reaction. And so this is solid copper, and then this would be 1 molar copper plus 2 solution. And here, the solution then is turning into the solid. Copper 2 is turning into copper solid. All right, so let's go ahead and talk about anode versus cathode. Cobalt 0 to 2 is oxidation. Who remembers what oxidation occurs at? What does oxidation occur at, anode or cathode? The anode. Anox, red cat. Remember that? Another way to look at it, vowels and consonants go together. So reduction occurring at the cathode. I don't want that thing to throw you off because that is not a negative. Let's cut that. No, I want to cut it, not copy it. Okay, so reduction always occurs at the cathode. When we talk about electrolytic cells, it's going to be the same thing. So you can always depend on reduction occurring at the cathode, oxidation occurring at the anode. The point of this cell is to get electrons to flow. And so through our wire, we could put something at this point. We could put a voltmeter here. We could put a battery. We could put all sorts of things. But as the electrons, you don't want a voltmeter? Physics, is that why? I'm sorry. Sorry. Yeah, we can make it something else. What do you want to make it that's not physics related? A light bulb? Y'all didn't light any light bulbs?
We did, but yeah. I have to only think about 1 ohm mark as opposed to this weird. What is the resistance for a voltmeter?
I got it. Okay. No, we don't have to worry about resistance. That's taken into account in our voltage. We're fine. Don't worry about it. The point is, electrons are going to flow because of the potential difference between the 2 half cells. So the question is, which way do electrons flow? This is where the little oil rig might be helpful. Oxidation is losing, reduction is gaining. You can also look at the equations. This is losing electrons. That is gaining electrons. So electrons are going to flow from what electrode to what electrode? Anode to cathode. So that is always and forever the case. They always and forever flow from anode to cathode. So you need to, on the wire, indicate the electrons flow from anode to cathode. You can think they flow alphabetically. A to C, O to R, okay? That is always and forever true. One thing that's important that you do not do, and I've graded this question about 4 or 5 years back. The years start to flood together after a while. We had students who did this. That's how the electrons go. And I understand that's what they meant, right? But the professors there were like the old grumpy ones were like, no, that indicates they think it goes through the glass. I'm like, yeah, I'm sure that's what they're thinking. So no, you got to make sure you indicate that you know it goes through the wire. Okay. I was like, so what do you think? There's like a little diving board, and the kids think the electrons like dive off the diving board and then crawl back up. It's like, I don't understand. They're like, that we can't make any assumptions. So take that note when you're writing your AP. You can't make any assumptions about the grader. We have to pretend you know nothing. So make sure the electrons are going through your wire. So this cell, although it's working, it's only going to work for like one electron moving. One electron is going to go from here to here, then all of a sudden it's going to stop. No more electrons are going to go. Because why would an electron go to a place that's negative, right? And why would an electron leave a place after it's become positive? So once one electron leaves, this is positive, left side's positive, right side's negative, why would more want to go? So we need something to neutralize that charge buildup, and that is called a salt bridge. Now, the salt bridge is basically just a source of ions where the ions will naturally migrate. Once an electron goes over, ions will migrate to the appropriate sides to neutralize that to allow the ions to keep flowing. So we want to put something in that salt bridge that will not muck up any of our other ions. We don't want to put a sulfide in there because then we're going to get cobalt-2 sulfide or copper sulfide, these black solids that are going to start to pull that stuff out of solution and mess up our battery. We want something that's always, always, always soluble. So what are some things that are always soluble? Sodium nitrate, bromides. Are halogens always soluble? No. So I wouldn't pick halogens, but the sodium in both cases was good. Why? Group 1, right? And then you mentioned the nitrate. Aren't nitrates always soluble? So our safest bet for our salt bridge is a group 1 nitrate. Is that required? Do we always have to do that? No. You can do something that you know is not going to dissolve, going to cause a precipitate given here, but why not use something that you know will never do anything wrong? So group 1 nitrate's the way to go. We'll go with what I heard JD say, sodium nitrate. All right. So part of what you have to be able to do is indicate what ions migrate to which beaker. If electrons are going to the cathode, that's going to make a negative charge buildup on this side. If we have a negative charge buildup, which of the two ions are naturally going to go, hey, I like that, I'm attracted, I'm going to go that way? Na+. So the Na pluses are going to migrate down into that beaker. And then over here, we have a positive, because electrons left, making this positive. So what ion do you think is going to be happy to migrate down there? Yep, our nitrate ion. So definitely indicate that. They learned a good lesson when they wrote this question, because it was the first time they really asked about ion migration. And they had this written as like cobalt-2 nitrate. And so when students are like, nitrates will migrate, it was unclear to them whether they meant these nitrates or nitrates in here. So they ended up accepting a lot of different things. But that was a good learning experience. They should use a different ion if they don't want it to get confused. So anyway, are we good so far? Okay, the next thing you have to do is label our battery. How do you know how to put your batteries in your remote control or whatever? Positive and negative. I don't want you to think of these as literal charges because they're not. Okay? The reasons electrons move is because of a potential difference. It's not because it's moving to something charged. It has nothing to do with it. So don't rationalize it or try to rationalize it, because when we get to electrolytic cells, the opposite is true. All right? So I want you to literally just think of these as labels. It's a universal understanding. Kind of like, have any of y'all jumped your car battery? Tell me about that. How are those things labeled? There's positive and negative, but most commonly people look at the red and the black, where red is commonly the positive and then the black is the negative. And y'all know you don't have to hook the positive. You could put the black on the positive as long as the black is on the positive on the other car. They just have to be the same. So don't like think you have to put it that way, but that's just kind of a universal indicator of how to go. So universally, our anode is our negative side and our cathode is plus. Most people like to think of this as cations are positive, so the cathode's positive. Yeah, in this case, but not in the next case when we get there on Thursday. And the anode is labeled negative. Another way to think about it, there's a big T in cathode. That's positive. Okay, so there's your label. So the next thing I want to talk about is this battery is eventually going to die. It's not going to go forever. What two things could run out and lead to this battery stop working? No, the salt bridge is pretty free-flowing. You got to be more specific by looking at the equations. The solid cobalt, okay, copper 2 could run out. All right, so the solid cobalt literally dissolves into ions. So this is the case in all anodes. All anodes shrink. And this is my claim to fame. I came up with this. If anyone else says they did, they lie, because I own the rights to this. Anode shrinks because they're anorexic. Okay? They shrink. Fat cat. Cathodes, look what happens to them. They get bigger. So they're going to increase in mass. Why this is important, sometimes they'll give you a question on the test where they won't say anything but, this electrode increased in mass by 0.5 grams. And they don't tell you anything else in order to give you hints about oxidation or reduction. So you have to know that the cathode gets fat and the anode shrinks. Okay? So yeah, we could potentially run out of each of those. So if we run out, and let's say this were a rechargeable battery, does anyone know how that works? What a rechargeable battery does? Yeah, it forces, you use the electrons from the electricity to reverse the flow, regenerating your copper 2 ions and regenerating your cobalt solid. Something else happens you can observe. We have big color changes going on in the solutions. Copper plus 2 is pink, and cobalt plus 2 is pink, and copper plus 2 is blue. So what's happening to my pink color as the reaction proceeds? Gets more intense, and the copper plus 2 gets lighter. So you'd actually visibly see that color change happening if you were running this cell. All right, the last thing we have to be able to do is do something called shorthand notation, where you're going to write a little sentence that describes the whole cell. So it's always oxidation, double line, and then your reduction half cell. Run to the OR. Those of you who watch Grey's Anatomy, best show ever. It's awesome. It's a good show. Even though now I'm kind of sick of it, but I've invested too many years of my life to not watch it anymore. So I gotta keep watching it. Even though we had a good episode last week, I liked it. So you go to the oxidation equation. The very first thing you see is cobalt. Then you draw a line, and the next thing you see is cobalt plus 2. That's it. That describes everything you need. It's telling you what's oxidized. It's telling you how many electrons just by that information. Then you draw a double line, and then what do you see in the first in the reduction reaction? Cu plus 2, and then Cu. And that's it. That's shorthand notation. So I should be able to give you a piece of paper with only this written on it, and you give me all of that. You can have a voltage table as well. I won't make you memorize all the voltages. One other thing, if you have don't write this down, but if you have a concentration like 2 molar or some concentration other than 1 molar, it's going to be indicated in parentheses after the ions. But if nothing is written, it means 1 molar. Okay? All right, ready to do it again, but this time much more quickly. But we got a difference here. Does anyone see the difference between here we have a cell is made from copper and copper plus 2 and iron plus 3. Look what they gave us in the last problem. The reaction. So what are we missing here? Well, the reaction, I know that, but what do we got? What information did we get from the reaction? Yeah, we need to know what's oxidized and what's reduced in order to find the voltage, right? So whenever you're in a situation like this, my suggestion is go ahead and write both as reduction, and let's compare their values and figure out the one, take the one that has a higher reduction potential, that's going to stay reduced, and we'll flip the other one. So how do I write a reduction half reaction? And again, remember, we want a positive E at the end of this for it to be a battery. How do I write a reduction half reaction from copper and copper plus 2? Reduction. Half reaction. Plus 2 electrons makes copper. And I know this is 0.34 volts. And then we have iron plus 3 electrons. And I know these are both reduction. I get that. But I want to know what that value is. What is the reduction potential for 3 to 0 for iron? Negative 0.04. So of these two, which one is more apt to be reduced? The copper. So we're going to leave this one reduction, and we're going to flip this whole guy and make it oxidation. What also do we do when we flip it? Change the sign. So we get a 0.38 volt, and that's our E naught for this reaction. So now that we've done this, we can now start drawing our cells. Whoa, I don't want to lose them totally. So I want to put, just so you don't think electrons always flow to the right, I want to put reduction here this time, oxidation here. So this one's going to be the cathode, and this one's going to be the anode. And what's a half reaction for reduction? It's our copper, correct? And then this is iron goes to iron plus 3 electrons. Having those equations there are good because you get to, it'll give you the ability to answer questions about what's going on in the half cell. So here, ding, 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 here, the wire. What metal is this? Copper, and it's in 1 molar copper plus 2. This is iron, and it's floating in 1 molar iron plus 3 solution. Which way are electrons going to flow? From what to what? Anode to cathode. So this time they're flowing that direction. The anode is what sign on the battery? Negative. This is positive. We need a salt bridge because it's not going to go very long. What group 1 metal do you want to use? Oh, you guys are just so creative today, thinking out of the box. Is iron 3 phosphate? Iron 3 phosphate's not soluble. It is in an acidified solution, but we don't have that. Right, but phosphate's going to make. Right. Oh, and in regards to creativity, if it works, it works. Sure, you can always use sodium nitrate, JD. Go for it. All right. What ion migrates into the ion migrates into the copper half cell? Na+. Now, here's the thing that irritates me. Here's what I hear some teachers teaching their students across the country, and then I hear the students say it. Oh, the positive goes to the positive electrode. First off, that's just a way to memorize it, which is dumb, because I really think you guys can look at the direction of electron flow and figure out with common sense. So don't be memorizing stupid things that you may hear. All right? I want you to rationalize the ion movement. It's super important. And then that leaves behind a positive on the right cell, so the nitrate is going to naturally migrate into that cell. All right. What happens as the reaction progresses to the copper metal? It gets deposited on. It gets bigger, and that means the anode shrinks because it's anorexic. It's going to be less and less in mass. It literally dissolves away. Okay? All right, shorthand notation is the last thing. Run to the OR. What do we see first? Iron. O, oxidation first, then reduction. Think about electron. You could also think of it, I never even thought about saying it this way, but you could also write in order of electron flow. Iron 2, Fe plus 3, double line, Cu plus 2, and then Cu. Okay, das ist alles for today.